A 1 centimeter piece of aluminum traveling at 15 kilometers per second carries 50,000 joules of kinetic energy, the explosive equivalent of 12 grams of TNT detonating inside your station. That fleck of metal, smaller than your thumbnail, punches through reinforced hull plating like tissue paper because velocity squared dominates the kinetic energy equation. And at hypersonic closing speeds, physics doesn't negotiate. You're drinking recycled coffee in the habitation module when the universe decides you're done. The coffee bag is warm in your hand, tastes like metal, like everything up here, but the heat is real. Through the cupola, you watch Earth scroll past, blue oceans and white cloud banks 400 kilometers below. The station hums, a constant vibration you stop noticing 6 weeks into the mission. Life support cycling, solar arrays tracking, everything nominal. Then something hits the module at 15 kilometers per second and the laws of thermodynamics execute you. No warning. Ground-based tracking catalogs debris larger than 10 centimeters, roughly softball-sized, but the fragment that kills your station measures 1 centimeter across, invisible to radar, too small to maneuver around even if you'd known it was coming. The Soviet satellite it came from exploded in 1986, 40 years ago, scattering fragments into retrograde orbits. Your station orbits at 7.8 kilometers per second prograde. The debris travels the opposite direction at the same speed. Combined closing velocity, 15 kilometers per second. That's 40 times faster than a rifle bullet leaves the barrel. At that velocity, kinetic energy equals 1/2 mass times velocity squared. A 1.4 gram aluminum sphere, the mass of that centimeter-wide fragment, carries 157,500 joules at 15 kilometers per second. That's the energy released by detonating 38 grams of TNT. But the destruction doesn't come from the mass. It comes from what happens when aluminum, moving at hypersonic speed, encounters a solid surface. The impact generates pressures exceeding 450 kilobars, 450,000 times atmospheric pressure in the first microseconds. The aluminum doesn't punch a neat hole, it vaporizes instantly, creating a superheated plasma cloud at 10,000 degrees Celsius that expands like a shaped charge. The sound is a gunshot crack, followed by the roar of escaping atmosphere. The coffee bag rips from your grip and flies toward the wall. You see the hole before you process what it means. 15 centimeters across, not 1. The plasma jet from that tiny projectile blasted through the outer Whipple shield bumper, vaporized both layers, crossed the interior, and punched out the opposite wall. Edges glow red hot where superheated aluminum melted the hull. The module is dying, pressure dropping. 101 kilopascals to 90 in the first 3 seconds. The International Space Station uses multi-layer Whipple shields, spaced armor designed to fragment incoming debris, rated to stop projectiles up to 1.5 centimeters at 7 kilometers per second. Your fragment measured 1 centimeter but traveled at 15 kilometers per second. Kinetic energy scales with velocity squared, which means doubling the speed quadruples the energy. The shield that would have stopped this debris at orbital speeds fails catastrophically when closing velocities double. The outer aluminum bumper vaporized on contact instead of fragmenting the projectile. The standoff gap became an expansion chamber for the plasma jet. The rear wall, rated for 7 kilometers per second, never stood a chance. Alarm klaxons scream, red lights strobe. You've trained for this exact scenario 40 times in the simulator, but training happens in comfortable gravity where you can think. Here, in 0G, with pressure dropping and your ears popping, instinct screams run, and physics says there's nowhere to go. The station has 6 modules, crew distributed across 3. The impact hit the habitation module, which means the connecting hatch to Node 2 is 8 meters away. You launch yourself toward it, hands finding familiar grab rails, but you're moving through thickening fog as water vapor condenses in the dropping pressure. 80 kilopascals now. The air feels thin, like breathing at 6,000 meters altitude, except the altitude is increasing every second. You have 90 seconds from impact to zero pressure in a compromised module this size. That timeline assumes a 15-centimeter breach, which is what you've got. 90 seconds to reach the hatch, cycle through, seal it from the other side. But the other crew members, you count in your head while moving. Jensen is in the lab module, Chang and Rodriguez in Node 3 running diagnostics, Kowalski EVA-suited in the airlock, Petrov in the Soyuz running pre-undock checks. 5 accounted for. The 6th is Thompson, who is sleeping in crew quarters, which shares life support with the module that's venting atmosphere into space. The hatch to crew quarters is behind you, on the wrong side of the breach. Thompson has 90 seconds to wake up, assess, reach a pressure suit, seal it, and wait for rescue or make it to an escape pod. That's 6 tasks that require 15 seconds each under ideal conditions. Your hand hits the hatch control. The indicator shows green, pressure differential not yet critical, but you know the math. 70 kilopascals station side, maybe 40 in the HAB module by now. The hatch unseals with a hiss that becomes a shriek as higher pressure air rushes past you toward the breach. You pull yourself through, grab the manual override handle, haul the hatch closed against the pressure gradient. It takes both hands and all your strength. Metal seals on metal with a clang you feel through your skeleton. You spin the locking wheel, 8 turns, your hands shake. The pressure stabilizes. Node 2 atmosphere, 98 kilopascals. Survivable. Behind you, on the other side of 8 centimeters of sealed aluminum, the habitation module is already below 20 kilopascals, low enough that water boils at body temperature. The station's tracking data later shows 900,000 debris fragments between 1 and 10 centimeters currently in orbit. None of them are cataloged reliably enough to predict conjunctions. The debris you can see, the 34,000 objects larger than 10 centimeters that ground tracking monitors, those you can dodge with thruster burns and orbit adjustments. But the invisible fragments, the ones too small to track, they're out there traveling at 7 to 15 kilometers per second, depending on orbit geometry, each one carrying kinetic energy proportional to velocity squared. A 2-centimeter fragment at 10 kilometers per second, 280,000 joules, equivalent to 67 grams of TNT. A 5-centimeter chunk at 12 kilometers per second, 4.5 million joules, over a kilogram of TNT. And you can't see them coming. The comm system crackles. Chang's voice, tight with controlled panic, asking for status. You report the breach, the seal, the crew count. Jensen accounted for. Chang and Rodriguez safe in Node 3. Kowalski protected in his EVA suit. Petrov already sealed in the Soyuz. Thompson doesn't respond. The silence lasts 5 seconds that feel like 50. Then Petrov's voice cuts in, Russian accent thick with urgency, saying Thompson made it to the crew rescue vehicle. The Dragon capsule docked at Node 2's nadir port 30 seconds before HAB module pressure dropped below sustainable levels. 6 crew members. 6 survivors. Today. But the station is dying, piece by piece. The habitation module is a sealed tomb now. A 15-centimeter hole venting the last traces of atmosphere into vacuum. All equipment and supplies inside inaccessible until you can rig a patch and repressurize. It's 2 weeks of repair work minimum, assuming you have spare hull plating, which you don't because launch mass constraints meant choosing between redundant shielding and mission supplies. The debris that hit you was a statistical inevitability. Every year in orbit increases the probability that something in that 900,000 fragment invisible population intersects your trajectory at the wrong microsecond. Eventually, the statistics catch up. They always do. Whipple shields work by fragmenting incoming projectiles before they reach the pressure hull, distributing kinetic energy across a wider area. But the effectiveness drops catastrophically above 10 kilometers per second because the physics changes. Below that threshold, you get fragmentation, solid chunks that the rear wall can absorb. Above it, you get vaporization, plasma jets that pour through gaps in the shield like water through a screen. The ISS shields were designed for the average debris environment, 7 kilometers per second, mostly prograde orbits, fragments under 1.5 centimeters. Retrograde debris, objects in opposite direction orbits, represent less than 5% of cataloged objects, but they carry double the closing velocity and quadruple the kinetic energy. You don't design for the outliers because the mass penalty makes the station too heavy to launch, so you accept the risk. You calculate that the probability of catastrophic impact during a 15-year operational lifetime is less than 2%, file the report, and hope the universe doesn't roll a 98.
The universe rolled a 98. Today, you're alive because you were 8 meters from the hatch when physics decided your number was up. Thomson survives because he woke up fast and moved faster. But the station is permanently compromised now, operating at reduced capacity, one module down, and the debris field that killed it is still up here, still orbiting, still waiting for the next intersection of trajectory and bad luck. Humanity has launched 9,000 satellites since 2004. Each one eventually fails. Each failure creates more fragments. Each fragment collision creates exponentially more debris. We're building a shell of shrapnel around Earth that makes orbital operations progressively more suicidal, and the armor we design protects against the threats we can see, while the invisible fragments do the killing. You float in Node 2, hands still shaking from adrenaline, and run the math. Kinetic energy equals 1/2 mass times velocity squared. At 15 kilometers per second, a fleck of paint carries enough energy to crater a window. A 1 centimeter fragment becomes a grenade. A 10 centimeter chunk becomes an artillery shell. And there are 900,000 of them up here we can't track, traveling faster than bullets, each one waiting for geometry and velocity to align. The station survived today. 6 crew members made it to safe modules or escape vehicles. The odds favored you, this time. But physics is patient, and statistics are inevitable, and eventually every station in low Earth orbit loses the lottery against debris it never saw coming.